This will be the first in a series of lectures from Chapter 5. In Chapter 5, we're going to learn about the operational amplifier, and we'll learn about the basic functionality of this device, and we'll see some example circuits that can be built using the operational amplifier. This will be a fair bit of a deviation from what we've seen in the first 4 chapters of your textbook, in which we have primarily focused on resistor networks, looking at circuits that primarily just involved resistors and voltage and current sources. Now we're going to be involving amplifiers, but once we learn the basic functionality of the ideal op-amp, we will actually be able to use a lot of the same techniques to analyze them as we have learned in previous chapters. So without further ado, let's start talking about the operational amplifier. In industry, they typically refer to this as an op-amp, and that's just a shortcut for operational amplifier. And what it acts like is a voltage-controlled voltage source. So we've talked about dependent sources before in this class, and so you can consider the op-amp as a voltage-controlled voltage source, and depending upon how resistors and voltage sources are connected to the amplifier itself, the behavior of that voltage-controlled voltage source will change. But it will still follow some fundamental rules of an ideal amplifier, as we'll talk about in a little bit. It, used in combination with other elements, can help it to be made into various types of dependent sources. So you can combine this not only with resistors, we can also combine them with capacitors and inductors, which we'll see later on once we introduce capacitors and inductors in a future chapter. And so it performs various mathematical operations on primarily analog signals. We typically don't use the op-amp with digital signals. We're primarily focused on analog signals here. And so there are some different terminals that you need to know. This is the schematic for an op-amp. You may or may not see these offset null pins noted on there, but every op-amp has an inverting input, that is what is designated with the minus here, and a non-inverting input, that is what is denoted with the plus, and it also has an output. So you may see it just depicted as a triangle with a minus input, a plus input, and an output. It will also have positive and negative voltage supply rails, and so we see V plus in this particular op-amp, it's on pin 7, and then we see V minus down here, which is on pin 4. This particular op-amp is in this dual inline package chip, which has 8 pins on it, and this will be similar to the one that you're going to be using in the lab. We'll actually be using 2 different op-amp chips in the lab in this class, and so one will be very similar to this one here, and it's important to note how you count pins on an op-amp or any dual inline package chip. Pin 1, if you notice where this little notch is, there will actually be a physical notch. Sometimes there's a dimple in the top of the package, and so if you orient that so it's up to the top, then at the top left is pin 1, and then it goes up through pin 4, and then you take this U-turn and you see pins 5 through 8. And for this particular op-amp, your inverting input is on pin 2, your non-inverting input is on pin 3, and your output is on pin 6. Those are the most important to pay attention to, and we of course also need to power the positive and negative voltage rails. We'll talk more about that in a little bit. Some op-amps have pins that have no connection at all, so pin 8 is just there to make it look balanced and to have the same number of pins on both sides. And then some op-amps have, like we see on pins 1 and 5, something to balance it, or sometimes called an offset null input, and those are basically just used to tune the op-amp to make sure it is behaving as close to ideal as possible. So we'll talk about the ideal op-amp here in the next few slides. So powering on an op-amp, this is typically how the voltage rails will be powered, and so what they do is provide a power source to the amplifier, and so the output cannot be any greater than your positive voltage rail, and it cannot be any less than your negative voltage rail. Typically, for a lot of the op-amp circuits that we're going to analyze in this class, you will assume that the voltage rails are at plus and minus infinity. And so you're just going to be calculating gains assuming that you can stay within those voltage boundaries, and those voltage boundaries are sufficient. But as we'll talk about in a future slide, those voltage boundaries are important and do dramatically impact the capabilities of the outputs of your amplifier circuit. So in this case, we have a positive voltage rail, a negative voltage rail. Typical values for that, you might hook up plus and minus 10 volts, you might hook up plus and minus 12 or 15 volts. Those are very typical output voltages right there, very typical rail voltages. And so most of them will use two voltage sources with a ground reference between them. And typically we also often balance these. So we don't want, let's say, plus 10 volts and then just going down to minus 5 volts. They typically act as a pair to where whatever your positive voltage rail is, that same negative voltage is your negative voltage rail. So your output voltage is based upon a difference between the non-inverting and the inverting inputs. And so there is a gain, which we will denote as A. A is multiplied by the differential voltage, that is V2 minus V1, where those are your voltages as seen at the inputs to the amplifier. Now typically we will have some feedback on that, and that will keep this from going unstable, because A is actually called the open loop gain. That only applies if you don't have a loop that comes back from the output back into the input. So if you're just running it and just hook up some voltages, you can get it to saturate, because this A is actually a very large value. Ideally it's infinite. And so what's going to happen is you're going to multiply a very large value by any sort of difference there, and that's going to either be well above your positive voltage rail or well below your negative voltage rail. And so if you don't have feedback, your output will go to one extreme or the other. That's very useful for things like comparator configurations, which we'll talk about later, which allows you to compare one voltage value to another. But for most of the things that we're going to be dealing with, we are going to have some feedback, and so our differential there is going to be small, ideally 0. In real devices, you can't actually get anything to be infinite, and so typically it's very high, on the order of 10 to the 5th up to 10 to the 8th, and this is volts per volt. Remember, we're talking about multiplying a voltage here, so it's how many volts output do I get per volts of differential. So typically your gain is unitless. If you think about dividing volts by volts, the units actually cancel out. So our gain is unitless. Here are some typical ranges. This is from your textbook for op amps. Your open loop gain 10 to the 5th to 10 to the 8th. Your input resistance, as we'll talk about, ideally should be close to infinity. In reality, it's 10 to the 5th up through 10 to the 13th. Your supply resistance, or on your output, that is going to be very small. Ideally, it would be 0, but typically it's 10 to 100 ohms. And then your supply voltage is usually anywhere between 5 to 24 volts. So those are your voltage rails there. So feedback is very important. Feedback takes on the functionality of actually taking the output from the amplifier and putting it back into the input of the amplifier. This basically allows you to figure out if you are gaining the way you intend to gain. So if you're trying to output, say, an audio signal, feeding back in some of the output audio signal allows you to know, did I get to the gain that I wanted to achieve? Typically, we put this back into the inverting terminal because that is considered the negative on the amplifier. That is called negative feedback. Negative feedback allows us to stabilize our output. So we're basically taking the output as a difference coming back in relative to the other signal coming in. And if we look at that signal relative to the output, we're trying to stabilize the output by feeding it back. Depending upon what elements the signal passes through, this could change the gain and the behavior. So typically, our feedback is going to come through a resistor. You might also have feedback coming through a capacitor, or you may even have it coming through a wire. And we'll talk about how to analyze these kind of circuits later on. Positive feedback actually leads to a lot of oscillations and helps the output to become unstable. Positive feedback, as an example, is if you've ever been to a concert or seen somebody make an announcement and they happen to have a microphone right in front of a speaker. Well, and sometimes you hear that reverberation where it just gets louder and louder and louder and becomes unstable and ultimately squeals. So if you're amplifying your output there and amplifying it again and again and again, then what you're actually seeing is positive feedback, and that leads to unstable output. So it's very important that we primarily focus in this class on negative feedback. Let's talk about voltage saturation. So typically, as I mentioned, the output voltage for an ideal amplifier is going to be unlimited. You could go all the way up to positive infinity down to negative infinity. In reality, it's bounded by those voltage rails that we talked about before. And so typically you can look at this right here. If you hit an output voltage that is going to be less than your negative rail, then you have what's called negative saturation. If your output is supposed to go to a voltage that is bigger than the positive rail, then you have what is called positive saturation. And so this is also referred to as clipping. So if you have an output that is supposed to be greater than, let's say, 10 volts based upon your calculations, but your supply voltage is only at 10 volts, the maximum you're going to see is that positive supply, and so you are going to actually see some clipping. And so I'll illustrate this better for you in class. You can think about it, if you had a signal that was like a sine wave, if you were to amplify and amplify and amplify that, it would get bigger and bigger and bigger, but eventually it would get so large that the tips of the sine wave would actually be cut off. And so it's important to recognize what your voltage rails are and what that's going to do to your output. So let's talk about some characteristics of the ideal op amp. We've already mentioned some of those. We want to have an infinite open loop gain. So ideally we want to be able to multiply a differential between the positive and negative input voltages by infinity, and that will be our output. The resistance of the two inputs will also be considered infinite. In a real world, it's just going to be very large, as I mentioned before. And so what that means is that for an ideal op amp, we will have no current flowing into the plus or negative input on the op amp. And that will be very important once we start analyzing some of these typical configurations. This will make a lot more sense once we get into the next video where we actually analyze some of these configurations. It will give zero output impedance, so zero output resistance. So that means that you will have no signal loss coming on your output. And so from the Thevenin's theorem, we can actually see that means that it is load independent. So you can have this whole thing basically simplified down to a Thevenin equivalent circuit, and then you can put whatever load you want on there, and the output voltage will be the same. The ideal op amp also comes pretty close with modern day op amps. Modern day op amps have very large gains, typically greater than 1 million. They have output and input impedances that do match the ideal. You can have input impedances that are often in the giga-ohm or tera-ohm range. And that means that things are behaving more and more closely to the ideal, even in the real world. We're going to work with some real-world op amps in the lab, and so you'll be able to see how closely these things behave to the ideal. And when operated in negative feedback, the output adjusts so that the two inputs have the same voltage. That's what helps us to stabilize our output there. So we will get in the next video into analyzing the inverting amplifier. I want to pause right here, but before I do that, I want to just showcase this is an inverting amplifier configuration. Here is our output. Here is our inverting input. Here's our non-inverting input. And you'll notice here we have a feedback resistor labeled RF. That is providing negative feedback because we have a feedback loop from the output back into the inverting input. So what that means is when that happens, we now have the same voltage here as we have down there. That's the whole purpose of the feedback loop. We can also say that we don't have any current flowing in here, and we don't have any current flowing in here because this amplifier ideally has an infinite input resistance. And so if you have an infinite resistance here, you can think about that as being almost an open circuit in here, and so no current is going to flow there, no current is going to flow there. So I'll stop for now, and this will be the first video introducing the ideal amplifier. In our next video, we're going to begin here and start analyzing the inverting amplifier configuration.